as we measure the position of something that's accelerating, if we look at that position versus time graph, we saw that the graph itself was a parabola because the acceleration caused the velocity to change, and so the slope changed. When we have a velocity versus time graph for something that's accelerating at a constant rate, and we'll start out with constant acceleration just so we can kind of get a picture of what's happening. There, let's say it starts out with some initial velocity v0, and that velocity changes to a final speed v over a time t. So it accelerates from an initial speed v0 to a final speed v, which is v0 plus at. Now, if we want to find the displacement for the object during that time interval t, we remember that the displacement is equal to the area under the curve, the integral. So what you see is that that shape is a trapezoid. So it's kind of, you have the two different sides. So the area of that trapezoid is half side 1 times plus side 2 all multiplied by the base. Or you can actually think of it this way. If you kind of cut right down the middle, when we have a constant slope here, we can cut the upper part of that triangle and fill in that space. And so we get that the rectangular area is our average speed multiplied by the time. And the only time we can do the average speed as final plus initial divided by 2 is when it's constant acceleration. None of the other times we've dealt with it before have we had that type of acceleration. So if you look at it, that gives us the average velocity, 1/2 v plus v0. That means our displacement, delta x, is just 1/2 v plus v0 quantity multiplied by the time. So the units of that are still meters. Everything works out. And so that's another one of our equations of motion. Our object has moved a certain distance, a certain number of meters in a given amount of time while moving at an average speed. So sometimes this is called the medium speed theorem, a median speed theorem out of the textbook, but it's just using the fact that the displacement is that area under the curve. Now, we started with our definition of acceleration, where the final velocity is the initial velocity plus the acceleration times time. So how fast you're going at the end equals how fast you were going at the beginning plus how much you sped up or slowed down. So what I can do is I can take my second equation of motion, the displacement, and then I'm going to do a little bit of substitution. If you notice, I have v in the equation here, and I can replace the v in the lower equation. And so now that becomes v0 plus at plus v0. We can group those together, and you get that our displacement we can write as v0 times t plus 1/2 at squared. So I haven't really done anything different. It's just another way of explaining the acceleration, the motion based on the acceleration, given different variables. So this will be our third equation of motion. So our final way of solving for the motion of an object is where we don't necessarily know the time. So what we're going to do is we take our first equation and solve for time. We subtract v0 from both sides, divide by acceleration, and then we're going to plug that into our second equation, delta x equals 1/2 v plus v0 times time. So we plug that in, we get 1/2 v plus v0 multiplied by v minus v0 all over the acceleration. So I do a little bit of algebra. Remember, v plus v0 times v minus v0 is v squared minus v0 squared, all over 2 times the acceleration, because the 1/2 I pulled it in. And now I can rearrange this to get this in a form that's a little more standard, and it looks like this. V squared is equal to v0 squared plus 2a delta x. So these are what are called the equations of motion. So these 4 standard equations of motion are what we're going to use to solve problems involving accelerated motion. Cars speeding up, slowing down, moving back and forth as they travel. But these are all related to the area under the graph. They're related to how we measure position and time when an object is accelerating.